Well, welcome to getting started with the Android NDK. So this is usually trivial. This is usually a topic that a lot of people don't like talking about because the NDK and C++ in general with Android development can be very tricky, super powerful, but there's definitely not, you shouldn't use this all the time, and we'll get into much more details about this. But my name is Mozart, Mozart Lewis, like the composer, the actual pianist. And I am an engineer at Button. Button is based in New York. And we're going to talk about some very fun things that if you have existing C++ code or writing cross-platform applications or high-performance applications, how to get started with the NDK and what it looks like and how troublesome it can be sometimes. So what we'll be covering is what the NDK is. We'll talk about an overview and talk about the JNI, which isn't new, but how it's used and everything that goes around it. CPU architectures, ABIs, and an age-long taboo of live coding, just a little bit, not too much. Then we're going to talk about when should you actually use the NDK. This is not something that you should be using all the time, but when does it make the most sense? Because while you can write your entire application in C++, if you really wanted to, it's usually not recommended for a lot of reasons. And then we're going to do a little bit more coding because one of the many tricky things, or the most tricky thing in my opinion, is actually calling Java methods from C++ itself. So let's say you want to access something like the Android ID from C++, and so how do you actually get that information using the JNI? And it can be a little tricky, and if you're not careful, you can cause a lot of crashes, or your development cycle can be very, very, very interesting. So what is the Android NDK? And this was stolen straight from Google's first welcome to the NDK page. But the NDK is a tool set that lets you implement parts of your app in native code using languages such as C++. So basically, using C++, C and C++, you can write that code for your Android application, and it will run. So the NDK itself contains a compiler. The default one currently with the latest version is Clang. And the standard C++ library that everyone knows about, C++ 11, 14, 17. R18B has support for C++ 17. Well, actually, let me ask a question. How many people have actually written C++? How many people have enjoyed writing C++? Okay, that's what I thought. The NDK now supports C++ 17. I think this came out recently. Probably with R17 or R18, the C++ 17, where you can do all these things like optionals finally in C++, but that's a whole nother land. So warning, I alluded to this before, but while you can technically write your entire application in C++, if you really wanted to, you probably shouldn't, because not only is the Android application framework there for a reason, but also writing your entire application in C++ really doesn't yield you any benefits more than just writing it in Java. And there's very specific cases where using C++ is actually better, but these cases are very specific, and we'll get into that right now. But I'll get into that a little bit later, because the next thing we're going to talk about is the Java native interface. So this thing, the JNI, it's not new. It's been here for a while, but it enables you to write native methods to handle situations when an application can't be completely written in Java, right? So when the Java doesn't support platform-specific features, or if you want to write cross-platform code, you want this C++ code to be able to run on iOS as well, have one shared code base. For instance, a lot of applications like games, for instance, are not rewritten in Android or rewritten in iOS. No, the code is all written in C++, and then they have specific API hooks for file system and how do you get certain IDs from the device that are only handled in the Java layer and not the C++ layer. And so what we'll get into is how this JNI is probably more of a really big bridge between your C++ code and your Java code. So when should you actually use the NDK? So the NDK is mainly used for high-performance applications. Everyone knows that C++, in most cases, is going to be faster than Java because C++ compiles directly to native code, while Java has to go through the JVM, then turns into bytecode, then has to go to JIT, and then it becomes machine code, and that whole process, nasty and long. While C and C++ compiles directly into machine code, right? So this is great for things like high-performance applications, CPU-intensive tasks, game engines. Most, if not all, game engines are written in C++. Why? Because most of them need to interface with OpenGL, which is a whole C stack, and all these graphic APIs are all written in C for their high-performance capabilities. So before we get into some code, I wanted to talk about some of the JNI types, because the JNI types are basically everything with a J in front of it. If you notice, like, byte is a J byte, and an int is a J int. It's nothing super special. It's just the JNI's interpretation from what Java's code will look like to what it will look like in C. And the same thing goes for like a J object, a J string, a J class, which we'll use these three. We won't use J throwable, but we'll definitely use these three, and you can see why the NDK does this. But it's, once again, like a weird, very weird, interesting situation. So what are ABIs? ABIs, so on your phone, I don't know if anyone like watches, like when they look at a phone, like, oh, what processor does it have? Oh, you hear like Qualcomm Snapdragon 835, and you'll see a Samsung Enos octa-core, blah, 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 right? So these are all CPUs, and if you've done operating systems or anything like of that, CPUs come with instruction sets, and those instruction sets are like what you hear like x86, that's Intel's CPU desktop platform, and ARM, you'll hear the ARM V7A and ARM 64-bit, all these different CPU architectures. So when you write C++, it has to compile for that specific architecture. So you'll hear for instance, Google is now requiring most applications to support 64-bit mode in like August or something like that of next year, which means that all C++ code has to be compiled and compatible with 64-bit processors, since I don't know if anyone actually makes any more 32-bit processors, but that's besides the fact. And so every single time you compile your application, it has to be compiled for a specific ABI. And this is really easy. It's really non-trivial to do this in Android Studio. It's just, this is something to keep in mind when you're developing, because there is certain cases where, let's say you're compiling the C++ code for x86 and certain things don't work because the instruction set is a little different, whereas it works on all ARM processors. And I've run into this, especially in game development, where you're trying to run a specific piece of code that won't run well on an x86 architecture, but it'll run well on an ARM architecture. But little nuances. What we're going to get into is very intro, nothing too crazy. It's just how you start writing C++ code. So here's a modern ABI list. Most phones currently have an ARM 64 V8. That's all the Snapdragons. It's a 64-bit processor. Although I don't know any personally, there are some Intel Android devices out in the market. I don't know much of them, but so you can decide if you want to support that platform. But for instance, if you want to run your application on an emulator, it needs to support x86. So let's actually look at some code. And as of the recent update of Android Studio, they've made it really easy to actually add support for C++ in like a brand new application. So we are going to try that now. So what this looks like, if you do like a new project, it'll be like new application, blah, 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 right? You click next. Well, this window's actually really large. I didn't even know that. But at the bottom, in your first create project, you have a chance, you can say, include C++ support. So we'll do that. I'm going to use Java initially and then show a Kotlin implementation afterwards. And so you'll go through like the same thing. Okay, latest API 19, cool. And blank activity, activity main, cool. And then when it'll ask you what toolchain do you want to use. So this is where you get to choose C++11, C++14. And I think if you use default, it'll allow you to use some features of C++17. Not all of them, but whatever the NDK supports currently. So you'll click finish, and then boom, your application starts building. And if you look at your folders, you'll find that beside the Java folder, there's a C++ folder, right? This didn't used to exist. You used to have to do this very differently in other versions of Android Studio, which is why I'm glad that they kind of added a lot of C++ support as of 3.2. But while this is building, you'll see that you have this native lib.cpp. And this is with like a blank project. So you'll see that happening, and it starts building. This might take a while to build, so I'm going to immediately switch to something that already exists and works. Boom. All right. So when everything is compiled, said, and done, see, this is why it's always an age-long taboo never to do live coding. Okay, give me 1 second. Okay. All right, there we go. All right, cool. So I have a simple app, right? What I'm going to show you is a simple app that is a calculator. And what it does is it'll use the NDK to actually do the mathematical operations, right? So here, this is Kotlin. I don't know why this is the version that's here, but this is fine. So I'm just going to show you the Kotlin version then. So what we have here is we have native functions, right? And so to declare a native function for your NDK or for your C++ code, you have to call a private external function, right? And then you add your parameters and your return type. And what this does is now it'll go into your C++ lib that gets loaded. So every single time this activity starts or when the application starts, you'll see here I have a companion object, and in its initialization, it loads a library called native lib, right? This native lib is going to be compiled when you're compiling your app. It gets compiled with all the C++ code, and then gets stored in a shared object, an SO file, right? And that SO file is what contains those functions that get linked to. So what happens here, if we go into native lib.cpp, right, I have this function right here, and it's an addition function. All right, can everyone see this? Is this good? Okay. So what happens is you see this very, 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 very nasty thing here, right? Now we can go very, very slow with this, and that's what I'm going to do. So you have extern C, right? That's basically saying we're using a C library, right? And JNI export, right, in a JInt. So this method matches what the main activity is declaring. So we're saying private external function add. I have two parameters, x, y, and they're both integers, and my return type is an int, right? So if we go to the C++, same thing. We have a JInt x, a JInt y, and we're returning a JInt, okay? Now, you're probably wondering why is the method name, why does it look like this? Why is it Java _com_ my entire package name basically, plus the class, plus the name of the actual method? Now, this is one of the things about the JNI. It needs to do this so that it can directly, specifically know exactly what to execute. This is one of the very cumbersome things about the NDK that makes it very nasty to work with, because if you spell this wrong or you do anything wrong, it'll crash and you might not notice this because the runtime errors are very, very not clear. But what ends up happening is I made a little cheat up here, and it's a macro that will do all of this naming convention for you so you don't have to do it for every single method. That basically is just a little cheat. And let me write some code. And what this does is I can go in here and pretty much delete all of this and say J method. My return type is going to be a JInt, and it's for the method add. So now that whole thing has been cleaned up, and this basically just gets replaced with this entire long line. So if we go back to our code here, and what's happening is we're just saying, hash result, not multiply. We're just saying here, oops. I forgot to do this in Kotlin. Yeeps. Hold on. This is why I don't understand why my Java version of this project is not opening. Okay. Okay, there we go. Very interesting times we live in with how live coding always fails you. Okay, so this is the same exact code, but just written in Java, which I already did ahead of time. The same exact code is just in Java, written a little differently. And so yeah, so we have the same exact issue here. And so what I'm gonna do is I'm just gonna run this application, which should already be good. And what's gonna happen is it's going to show you like the addition. Oof. Interesting, okay. This is interesting, all right. Okay. I think we ran into an issue with, once again, pretty easily, it's an easy issue with, you see how like that function, I probably spelled it wrong when I initially ran it. And so like it failed and it was just like, I can't run this. And we're gonna just try this one more time. And that's not the issue that I thought it would be. Okay, so I'm going to just delete some stuff here that I wrote that seems to be breaking this entire implementation. Okay, there we go. Finally, sorry. So many different things. So basically what I'm doing is, the NDK is going to be doing the addition, right? And so what happens is, you'll see 700 here. Now, how did this actually happen? This onCreate set text, I get the value of add, right? And add is a native function that goes into C++ and runs this method and says, okay, we're gonna do the addition in C. And then it's gonna return X plus Y. Now, if we go back to the slides, right? Was it necessary? You already just seen the troubles of getting this up and running and seeing that you mess up just a tiny bit, the whole thing goes to shit, and it's just like, what's happening? I can't even figure out what's going on. And is it really that much more performance in this specific case? Absolutely not. Java can do addition pretty fine, and it'll probably be as fast, if not the same, because it's a little more optimized. So there was no reason to really go and do a simple calculator where all of your methods are in native C, right? So once again, I'm bringing this slide back up to say, like, when should you actually use it? you need to use it in very specific cases that we're gonna actually go into a little bit, where it's actually being beneficial. Like, so for cross-platform applications, ones that require OpenGL and something for super high performance, but you don't want to rewrite your entire implementation in Java, or you don't want to rewrite your entire implementation in Swift or in Objective-C, where you can write this in C++, and then both application, the same core will be in C++, but then it can run on both Android and iOS, and it'll run on native. So most applications, like I said earlier, like games, most of them are either written with a game engine, which backend uses the NDK to compile for Android. So here's a short video of Tensor-flow, right? And Tensor-flow, what happens is it's an object recognition. So this is telling, I don't know if you guys can see that. Whoa, it's playing for me perfectly here. Oh, okay, there you go. So you'll see it's kind of recognizing what objects on the screen, and that's using TensorFlow. I'll play it one more time. So using TensorFlow, it's like, it looks at my computer, it's like, okay, this is a notebook, this is a laptop. And I go to like a water bottle, it's like, oh, this is a water bottle. And so how is this actually happening? How is the image coming from the Android camera, going into the JNI, and then going into the C++ implementation of TensorFlow, and coming back with results saying, hey, this is what it is. So I drew this little image that kind of shows you exactly what it is. So, we'll go in here, and there's a classifier. The classifier will call to the JNI and say, here's a bitmap, right? The bitmap then goes to the JNI, right? And the JNI is like, okay, classify this actual image, right? Now, TensorFlow itself, the actual library is cross-platform. And all the JNI is there to do is kind of a bridge. It's like saying, okay, I got this data, and I'm going to take it from Android, from Java, and say, go to the TensorFlow actual C++ core library, and with a pre-trained model, tell me what you see on the screen. The actual C++ is gonna run, and it's gonna be high performance, because we're doing every frame a second, whatever the case may be, and then it's gonna show you the top 3 results. That goes back to the JNI, and the JNI then calls back to Java and says, here's the top 3 results with confidence, and I can say this is what I think it is, right? And so this circle is a perfect reason why you should use the NDK, because TensorFlow now can be run, the same exact model can be run on iOS, where they can do the same exact circle, and they don't have to re-implement TensorFlow for iOS or re-implement TensorFlow for Android and Java. Instead, they can both use C++. And so just a little code of how they actually do this in the example. This is a Java method. It's converting a YUV image to an ARGB image, right? So it takes it and it says, okay, try to convert it with this one-line method that I have highlighted here. So this one-line method is a native method. It's been declared here, right? So this native method then, with all of its parameters, goes into here, the JNI export void image utils method convert. So now this is using all the JNI objects, JBooleans and stuff like that. But the actual code that's doing the conversion isn't in the JNI file. This is the actual code that's doing the conversion is part of TensorFlow. The JNI is there kind of as a bridge to say, hey, I'm receiving this data because I can understand how it's coming to me from Java, and now I'm going to give you the data to actually do the implementation. And this code right here is actually part of the TensorFlow library, which this method can be used both on iOS and Android. And so this is doing some interesting image conversion. And so that's one good case study of why to use the NDK. Then we have game engines. And I chose Cocos2d-x as the game engine to mention here because Cocos2d-x is written fully in C++, and it's completely open source. I've actually contributed to some of it for Android. And what Cocos2d-x really is, it's just a light wrapper around OpenGL. And so, has anyone here used a surface view before? Okay, and so when you're using your surface view, you look here. So this is Cocos2d-x's engine code, right? This is their main loop. This is run 60 times a second. So if anyone's a big gamer here, you know 60 FPS is kind of like the butter smooth, that's what you want to hit all the time, right? And so this needs to run consistently. So this is in C++ on Cocos2d-x. So how is this getting called, right, from Android? So there's a JNI class here where they're calling that native render, they're calling this line right here, main loop, they're calling it every single frame. So this is a JNI method. Now, how does this work in relation to what's happening in Java and on the surface view? Well, that native method is declared here. I don't know if you guys can see the highlight. And then on drawFrame, which is part of the GL surface view.render class, which basically says, for every single drawFrame that I get, call this native render method, which goes into the Cocos2d-x code and renders the actual frame and spits it back out to the surface view. So the model is almost exactly the same, where the renderer says native render on every frame. It goes in and calls the native render and executes a render, and then it calls main loop, right? And there's no returns in this case, but this is a perfect example of rendering every single frame and executing on the C++ side, where it's more efficient and it's better, because while you could do this in Java, first, you lose cross-platform, so you wouldn't be able to run this on iOS, obviously, if it was in Java. And then second, the Java implementation might not be as fast because OpenGL is completely written in C++. While OpenGL is already in the Android framework, it's already there, technically. They're just using OpenGL-ES, that's what the Surface View is using. But having it done here is allowing the cross-platform ability, where this can run on Windows, this can run on Mac, this can run on iOS. And so it's one unified code base with very small implementations that handle things like file system, things that are very specific to Android that can't be accessed in C++ otherwise. So since my live code pretty much went downhill immediately, I can try this piece again with Kotlin, because this one I'm pretty sure is good. So what I wanted to note here in particular is calling Java from C++. So now this is backwards. This whole presentation I've been showing Java going into the C land and stuff happening in C land. But how do you do this in reverse? And the reason why I call this cumbersome is because the way you have to define a method in the JNI to call back to C++, to call back to Java to get something is very, very easy to mess up. So we'll try this once, and we'll see. So I'm going to add 500 plus 5, and I have a method here called hash, right? This hash method, right, is a native method here, which you'll find here. And when you go into the native lib, go all the way to the bottom, I have my JNI method. It returns a JString and it's hash, right? So to look at this code carefully, what you'll realize is in order to call, what I'm doing here is I'm saying, OK, I want to hash. But the way I want to hash is I want to get the Android ID, right? And I have a method here called obtain ID, right? And it just returns a string. Don't do this, by the way, but for this example, I have it like this. So what I'm saying here is I'm like, well, I want that method to add to my hash, right? It's my SHA-256 hash. I want to add this as like a salt so that the hash can be a little bit more powerful and device specific. And so to do this, you have to get a class, right? And you get the class from the instance of whatever object is calling this. But then you have to get a method ID, right? And getting the method ID, you call this thing called environment, which is the JNI environment. And you try to get the method ID from a class, you give it its name, and then this last string here. Can anyone guess what this last string is doing? I don't know if I can zoom in.
Return type?
Yes. This last string is the return type. And as you notice, it's like this weird L, Java, lang string with a colon. This makes no sense. in my opinion. I don't know why it's done like this. It's obviously done like this so it can get to the exact package. I wish there was a more easier way because this is very easy to mess up, right? But if the method doesn't exist, we try to catch that and just return an empty string. Otherwise, then we get the result of that method. So it calls the Java code, Kotlin code, to actually get whatever the string that method is trying to return. And then we have to cast it from a J object to a J string. So it's a whole a lot of different things just to get a string from Java. But if done right, hopefully, yeah, see, I have absolutely no idea why this thing is exploding. Yeah, but what would happen is, actually, I already have the app precompiled in here. What happens is, it'll actually go and do that code, and you'll see, this is a long hash string, but this is all coming from C++, right? And so this is where, using the code that's in C++ is a lot easier to manage in terms of cross-platform and using the same exact code on both instead of relying on your teams to try to implement whatever you want the same exact way, both in iOS and Android. But you shouldn't use it all the time, for sure. But it's definitely a tool to leverage for high-performance applications, applications that use OpenGL, or, for instance, if you're writing a sound library, you would want to use the C++ instead of the Android Media. I don't know if anyone's ever worked with Android Media player, but it's not fun either there. So you can write C++ code to play audio and stuff like that. All right, well, thank you.